Hey everyone! Today we're talking about graphing rational functions. Now with this, your temptation is going to be to reach out for that graphing calculator and have it help you. But the point is that we're going to teach you how to do it without a graphing calculator. So while you may use your graphing calculator to practice while we're learning and double check your answers, please realize that you're going to be asked to do this without a calculator on quizzes and tests. Okay, let's get into it. Use a table of values to sketch a graph of the reciprocal parent functions. I see three keywords there, all of which we've seen before. Parent functions, we've seen those in their transformations, like x squared and the square root of x. And reciprocal, we've seen that too. When we start out with a whole number, that just means that we're going to put it in a fraction under 1. 1 over negative 10 gives us a negative 1 over 10. If we start out with a fraction, we can think about a reciprocal as just flipping what's on top and the bottom. So we flip it and we get negative 2 in this case. I'd like to draw particular attention over to the 0. We have talked about in class that in fractions we do not want a 0 in the denominator. We just can't divide by 0. If you plug it into your calculator, it'll tell you error. And we call that undefined in math. Another way to write this is DNE. That stands for does not exist. I will understand if you write any of these and will give you full credit. Now, if you've already, go ahead and fill out your table. And when you're ready to move on, the next step is to plot our points. Too far. There we go. Okay. Now, before we connect the dots, I want to get a little bit more information about what our graph looks like. You'll see over here we have horizontal asymptote. Asymptote, that's a word we've heard before. You remember back to conics? An asymptote is a line that a graph approaches but never quite reaches, never quite touches or crosses it. Now, to figure out what our horizontal asymptote is, there's a little mnemonic that can help us remember. Hoi, hoi vux. So hoi pertains to the horizontal. It says horizontal has a 0 slope, and we're going to write the equation as y equals. So I'm going to go over here. I already know that my horizontal asymptote is going to be y equals. Now, how do we figure out where a horizontal asymptote is? Well, what do you notice? It's interesting about our points. It seems to be getting smaller and smaller and smaller, and over here these values are approaching it, but it never quite reaches. That's because there's a horizontal asymptote at the line y equals 0. Remember, we're going to have a y equals. So let's go ahead and draw our dotted line. Let's go over to our lines to make a really neat one. And there's our horizontal asymptote. Now don't see quite where it is and don't believe me? We'll take a look. Let's go back to our function and see whether it makes sense. That means that we're never going to get a situation where y equals to 0. F of x, we can think about that as y. And in order for y to be 0, our numerator would have to be 0. But here it's 1. So that's never going to happen with our function. That's why it'll never cross this line or touch it. Y equals 0 is going to be our horizontal asymptote. Awesome. How about vertical asymptote? We have a mnemonic for that too, VUX. This stands for vertical, has an undefined slope, and we're going to write the equation as x equals. This one's a little easier to see because we're going to look at what happens when x equals 0. It's back to what we were just talking about. When x equals 0, we have undefined. Hey, that's what we're looking for right here with the u, undefined. So that means that at x equals 0, our function does not exist. And again, we have our dotted line because it's a vertical asymptote. We're going to approach that line but never quite reach it or touch it. And then I'll just write it in for us. X equals 0. Now this is some important information when it comes to our y-intercept and our x-intercept. Because our asymptotes are at x equals 0 and y equals 0, they're never going to cross or touch either the x-axis or the y-axis. So our y-intercept does not exist, and neither does our x-intercept. Domain we have experience with, so we'll just write this guy in as all real numbers, except we have that asymptote, so where x does not equal 0, and range similar except y does not equal to 0. Now the one last thing that I haven't done yet is once I knew my horizontal and vertical asymptotes, I can go ahead and connect my dots. Please make sure that you're trying to do a better job than me and actually hit your dots, but that's the general shape. And over here. Whoop. A little closer except for that last bit. And that's our general shape. Let's review how transformations are going to affect the reciprocal function family. You'll notice a lot of similarities to transformations that we've done before. Again, we have the A, which indicates a vertical compression or stretch. These rules follow similar to the square root rules, where if A is greater than 1, we have a stretch, and if it's less than 1, it's a compression. Remember, we're looking there at the absolute value of it. Absolute value of A. H, which goes along with X, is left or right. That's a way we can remember. Since it's next to X and X moves left and right, then that's going to cause our horizontal shift. And just like before, it's going to think opposite here. So if it says X minus 2, although our instinct is to go left, we do the opposite and move right 2 units. We'll get more practice with that. Then with K, that's the up and down. It's on the outside, goes with our Y, up if it's positive, and down if it's negative. Lastly, our reflections here are a little easier. We don't really have to worry about whether it's over the x-axis or the y-axis because of the special properties of our parent function. If you come back and look at it, think, what would this look like if we flip it over the x-axis? It would look something like this. A little curve this way and a curve this way. Now, what if you flip over the y-axis? Hey, you get the same thing. Curve over here and curve over there. So, the only thing you have to watch out for here is that if there's a negative out the front, you have to reflect across the y-axis for simplicity's sake, since it's the same thing as flipping over the x. Alright, now that we've gone over that, we can look at another example. It's a bit more complicated. First thing we want to do is list the transformations. First thing I notice is that we are going to go down 5. And then the other transformation is right here. Remember, opposites here. We're going to go left 3. This is key because it lets us know how our asymptotes moved. So remember, to begin with, in our parent function, the horizontal asymptote was on the x-axis at y equals 0, sorry, because hoi means y equals. So, but that whole thing moved down 5. So that whole asymptote is going to move down 5 and it now lives down here at y equals -5. Y equals -5. Oh, fun purple color. Same thing with our vertical asymptote. It moves left 3. So it had been at x equals 0. Now it is at x equals -3. From there, we remember the general shape of our parent function, which was a lovely little curve like this that approaches the asymptotes but never quite touches. And the same thing on this opposite side. And notice that I drew these two little dots, one square box away from where these asymptotes meet. And that's because we didn't have any vertical compressions or stretches. That's going to keep its same general shape. Just something to note. Our y-intercept here, we are actually going to have, because the asymptote's no longer on the x-axis or the y-axis. So y-intercept, that's where we're crossing our y-axis. How do we find that? Do you remember? Our y-intercept occurs when x is equal to 0, when it's along this vertical line, x equals 0. So how we can find it is plug in a 0 into your function wherever you see x. In this case, we have 1 over 3, because 0 plus 3 is 3, minus 5. You will find that your y-intercept then, which remember we write as a point-in-point notation, so it's going to be at x equals 0, and y equals -4 2/3. The x-intercept is when our y is equal to 0. So likewise, we go over to our function, plug in 0 for y, and solve for what x would be. When you do this, you find that x equals -14 over 5, and that's when y equals 0. Our domain, all real numbers, x is not equal to -3. All real numbers, y is not equal to -5. In our alternative notation, if you prefer, this is also correct. -5, infinity. Okay. Now with this next one, what I'd like you to do is go ahead and give it a try yourself. In a moment, I'm going to load up the answers, but it won't help you to just do another one without really thinking and trying to get it yourself, so that way you can see where we're still struggling and you can go back to the video and re-watch those spots where we're still not quite sure. Go ahead and take that time now, and then I'll load up the answers in a moment so that you can check your work. Okay, did you give it a good try? Here are the answers. Let's go through it quickly. The transformations were to flip over the y-axis, that's coming from this negative here. Nothing's going on with a horizontal shift, but there is a vertical shift, up 2. That means our horizontal asymptote moved up to y equals 2. Our vertical asymptote did not change since there was no horizontal shift. Our y-intercept does not exist since we still have that vertical asymptote on the y-axis. Our x-intercept, though, does exist. Remember, we find this by plugging in that y equals 0 back into our function and solving for what x that gives us. Make sure that you're practicing this and actually doing the work off to the side. Double check that you know how to get this number. Our x-intercept in this case is 1/2, 0. Our domain is all real numbers, x not equal to 0. Range, all real numbers, y is not equal to 2. That comes from our asymptotes, of course. Now the last thing I want to note is that when you're making these graphs, you can get some key information just from the beginning from your parent function, but then also use the y-intercepts and the x-intercepts to your advantage. Here, I used the fact that I knew that it was going to cross the x-axis at 1/2, 0 to draw myself a little point there when I was making my graph. Just a tip so that you can be as accurate as possible and gain the most points on your quizzes and tests. Now, really important, for number 4 and number 5, it is your responsibility to go ahead and finish working through these. To earn full points for your notes tonight, I will be checking that these 2 questions are completed. So this practice is mandatory. Make sure that you note that. All right, if you have any questions, please bring those in tomorrow and we'll talk about it. Have a great night.